Hi everyone, I'm Joon-Hwi from Caltech. I really much appreciate the opportunity to be here and present my work. Today I'm gonna talk about one-form symmetry in dynamical gravity, which I propose in this new paper with Clifford Chung, my advisor, and Ira Rostein at Carnegie Mellon, and students Maria Dorda, Vinicius Neville, and Nahasa. So basically, in this talk, I will propose and present or reveal new symmetry in our universe by taking insights from Yang-Mills theory and paralleling that with gravity. So first of all, I have to review what symmetry I will be revealing. That is a sort of a higher form symmetry. So let me explain briefly what this means. So symmetry in physics has been a unique guiding principle. So we learned constraints on kinematics, like insights on phase transitions, symmetry breaking, and all these. So symmetry has been like a very important topic. But from the textbooks, we usually only describe symmetries for local operators. So for instance, we know from the celebrated Ruhr theorem that when we have a symmetry transformation of a local operator with some representation of a group element, then we also have the conserved current. But there has been like a new insight, or well, it's not new nowadays, but very interesting insight, which is the conserved current could be kind of repackaged or rephrased in terms of a topological symmetry operator. So when we have a conserved current and then can integrate that current over a 3D volume or hypersurface to obtain the topological symmetry operator. And this symmetry operator encodes the symmetry in terms of the linking between the point and the hypersurface. So super concretely, it is encoded in the ward identity, which takes this form. So you insert the topological symmetry operator in whatever the hypersurface V you choose is kind of robust under like deformations, topological deformation, unless you kind of cross the surface across the point. So in the covariant formalism, this ward identity is like kind of established in terms of a path integral, but we can also approach in terms of the canonical formalism. So in the Hamiltonian perspective, the transformation precisely arises from like a sort of a commutator. But it turns out that we not only have the local operators, which are kind of supported on like points in our spacetime manifold, which I denote as M, but also operators that are supported on lines, and also higher dimensional supports. So in this case, the symmetry is kind of generalized, and we call those symmetries like 0 form, 1 form, 2 form, and in general higher form symmetries. So it turns out that the textbook notion, the earlier textbook notion of 0 form symmetry, is just a tip of a huge giant iceberg, and we then encounter a lot of more generalized notions of symmetry. But in this talk, I will be focusing on the higher form symmetry, and in particular to 1 form symmetry. So how does the higher form symmetries work? So for the 0 form symmetry, I explained that it is described by the linking between the point and the 3-dimensional hypersurface. If we increase the dimension of this defect operator by 1, and then the codimension of the symmetry operator increases by 1, so it becomes 2-dimensional in if the space-time is 4-dimensional. And this structure persists, and in general, we have p-dimensional operator linking with the d minus p minus 1 dimensional operator encoding the symmetry. So this is like a brief review of higher form symmetries. And now I'm going to talk about generalizing these notions to gravity. So why is this an interesting problem? Well, gravity is just fascinating. But there is another reason. So here, this is like a sort of like a literature review. And so far, most of the research on higher form symmetries has been kind of localized or like restricted to quantum field theories with no dynamical gravitation. And there are few works on gravity. That might be a reason why we have so like little number of works on gravity. And I can say that one worry that immediately arises is that linking between these like extended objects actually doesn't make sense if the gravity kind of like fluctuates and our space-time like radically fluctuates, and the linking just like, yeah, due to the topology change, the linking just can like break and it just doesn't make sense topologically.
That's a bit of a stretch.
Yeah, it's like kind of hand wavy.
No. Have you ever seen an example of topology change in your experience with gravity?
Well,
An effort.
no. Yeah. Yeah. But I would like love to explore more in the future. So yeah. So well, the resolution is to actually kind of retreat. So in this work, in this talk, I will just restrict my scope to the effective field theory regime of gravity, where topology and dimensionality of spacetime is preserved. But with still with this restriction, we still have like more things to explore. So there have been a lot of works on linearized gravity, namely under the name of like biform symmetries. But they are all kind of restricted to linearized level, while there are also works on the discussing the hyperform symmetries for in the context of the true non-perturbative quantum gravity context with topology change. But it turns out that there are still a room to explore, which is the effective field theory region of gravity, which is still nonlinear. So yeah, so basically we will explore this area, the nonlinear regime of effective field theory gravity, and discover a new symmetry in nature, and encounter very interesting consequences. So yeah, that's our motivation. So here's the roadmap of this entire talk. So first of all, I will very explicitly and concretely explain like a better resolution understanding of the one-form symmetry of Yang-Mills theory. So why do we have to spend like too much time on Yang-Mills theory? That's because I will show that the gravitational one-form symmetry could be immediately identified by kind of paralleling Yang-Mills and gravity, and this will sound very interesting to people who know about the double copy theory, actually. So yeah, so basically I will formulate gravity as much as possible, like Yang-Mills theory at the Lagrangian level, and just import all the known results in Yang-Mills theory to gravity, and that will surprise us, because importing the formulae in to the gravitational context actually reveals more interesting interpretations, like physical interpretation in terms of curved space-time geometries. So yeah, so that's our plan. So let me start with the first topic, which is the one-form symmetry of Yang-Mills theory. And namely, I will point out two lessons from this discussion. So first of all, let me start with the discussing the abelian case, which is just the Maxwell theory. So in this case, the Wilson loops are given by the line integral of the U1 connection, and the topological symmetry operator is kind of very explicitly written down in that formula. And in this case, the Wilson loops are labeled by the representations of the group U1, which are just integers, while the symmetry operator, as you can see here, is labeled, is kind of parameterized by some continuous parameter, lambda. But it turns out that in the Ward identity, the only thing that is appearing is the alpha, which is some the exponentiation of the real number lambda up to some customary factor of 2 pi. So alpha belongs to the group, and it labels a symmetry operator. So even though we have some like a little bit mild redundancy in the parameter lambda, the physical thing is the group element alpha. So that's why the symmetry operator is labeled by alpha, not lambda. And note that this symmetry operator could be kind of derived by observing that the star F defines like a conserved current, but that this kind of derivation of the symmetry operator only works for kind of continuous one-form symmetries, because for discrete one-form symmetries there's no conserved current. So for Yang-Mills theory, this should be not paralleled. So what happens for Yang-Mills theory? In this case, the Wilson loops are labeled by representations of the gauge group G, and the symmetry operator is often not stated explicitly, but it is defined in terms of the Ward identity like this, which states that the Wilson loop transforms with this factor, which is the representation of the center element alpha, to the power of the linking number between C and S. So this concretely kind of, this kind of defined the one-form symmetry, which is the symmetric transformation is given by that formula, and the symmetry operator is something that induces that transformation in terms of this Ward identity. But we can still question, like, can we be more explicit? So first of all, we can ask this question, like, what is this transformation of the Wilson loop? But in terms of the local degrees of freedom, like how does the gauge connection transform to make this Wilson loop transform in that way? So that's the first question. And second question is that what is this operator, this mystery symmetry operator, in terms of local degrees of freedom? And I will show that if we also introduce this lambda, like a color, which is a linear element, which exponentiates to the center element up to the 2 pi factor, then we can explicitly write down the symmetry operator, or explicitly realize the symmetry operator in this form. So let me explain the answers to these two questions. So first of all, we have to let us observe that the fact that the one-form symmetry does not transform any local operator. So in this, by this I mean that insertion of the symmetry operator leaves like operators, gauge invariant operators like field strength squared invariant. So how can this be possible? Like the one-form symmetry is kind of transforming like almost nothing, but only the extended line operator. So how can this happen? So geometrically, this happens because a two-dimensional surface does not link with a point in 4 dimensions. So the linking number between the surface and the point in 4 dimensions is not 1. But more concretely, I can say that the symmetry transformation takes the form of a gauge transformation. So that is precisely why the field strength square is just left invariant. But it should be not literally gauge transformation. So let me call this mystery transformation the twisted gauge transformation. So let me explain what does that terminology mean. So twisted gauge transformation, or TGT, is given by precisely the form of the gauge transformation, but with the gauge parameter omega being multi-valued. So if the multi-valuedness is characterized by the center element, where here the p plus and p minuses are those are points that deviate from up and below with respect to some branch cut of the surface of the symmetry operator. Then we kind of we can derive that the Wilson loop, which links with the surface S once, or in other words, intersects with the branch cut once, transforms in this way. So by direct algebra, we know that the Wilson loop at the endpoints it will transform with the omega and omega inverse. But we stipulated that the discontinuity condition of this multi-valued parameter omega is given by the center, characterized by the center element. And crucially, we can take out the center element outside of the trace, because the center, by definition, commutes with every element in the group. So geometrically, you can visualize this in this way. So intuitively, the symmetry operator inserts the representation of the center element at a point on the Wilson loop. But crucially, we stipulated that this operator is topological. So it like the branch cut should not be kind of pinpointed by any sort of like operation. So that kind of explains why the symmetry operator has to be be labeled by the center element. Next, I'll explain this explicit realization of the symmetry operator. So first of all, let me recall the fact that the word identity is kind of secretly.
Explain a little bit why you think it's gauge invariant.
Oh, the operator? It's a very sharp question.
No, it's a very basic question.
Well, I mean, that's a very question that confused us and for a long time and made us to put our paper. I mean, it delayed the schedule a lot. So our resolution is that even though this lambda A, which is a color reference, seems to break gauge invariance by being like picking up some color direction. Crucially, in the word identity, the exponentiation of this lambda is only appearing. So in this sense, this lambda is kind of spuriously breaking the gauge variance. It's like the color reference in the instanton creation operator is analogous to that kind of thing. In that case, we only talk about the instanton number change, not the specific polarization that we choose to put an instanton. And I would be very happy to discuss with you actually. Yeah.
So you agree that this operator is not gauge invariant?
I would say that this formula is like a particular realization of this this gauge invariant operator by picking up some reference.
Why do you need that? I mean, people wrote gauge invariant operators that do the job. So why do you need this gauge non-invariant?
This explicit formula?
Yeah. The other explicit formulas which are gauge invariant.
Like, for instance?
Well, you can roughly speaking take this formula and gauge average it over something to make it gauge invariant. So,
right. I think that's what Clay Cordova did actually.
I think this was done before Clay was born.
Right.
Not by a 12th.
I see. But we were actually not sure whether that averaging will make this operator like just 0 or something.
If it makes it 0, then it really means it's not gauge invariant.
Yeah. I mean, it's like kind of like
Take the average, you get something non-trivial and gauge invariant.
right.
That's the correct operator.
Yeah. So I think if you impose the center exponentiation condition and then average, then you'll not be there.
Well, the averaging is non-trivial. You have to figure out what to average over. You need to stick something else in there and then average over that. It's not completely trivial. But
yeah.
There's some version of this that works.
Right. And also I have some backup slides, but it turns out that to make this operator follow the group composition law, the representative lambda has to be picked in a very smart way, actually. So
that's putting the cart before the horse. If it's not gauge invariant, I'm not so interested in its group composition.
Yeah, but if you inserted this operator in the path integral, and then the resulting transformations are all gauge invariant, those loops. So yeah.
For the following, are you using the explicit form of this topological operator, or is it just like a side comment?
Well, for gravity, actually, this explicit formula becomes very interesting. Like, so, yeah. Actually, this problem precisely also happens for the instanton creation operator. So if you try to write down that operator explicitly, and then you will be also necessarily introducing some lambda like that.
I don't know what an instanton creation operator.
Yeah, but I think Tooth actually kind of explicitly wrote that down with some lambda reference.
In some dimension with some subtext, these words make sense. They do not make sense in 4 dimensions.
Let's see. Yeah.
There's something that is called a monopole operator, which is sensible in 3 dimensions, and which looks a little bit like this. In fact, that also involves averaging.
Right.
In the non-abelian case.
Right. Yeah, I think this is we're discussing, because we also have long time discussing this with, yeah, like internally, and then, yeah. So, yeah. But yeah,
But you're gonna use this later. I mean, it'll appear throughout your talk.
right. Yeah. But crucially, the wired identity, I mean, so we could have defined this symmetry in gravity, like axiomatically as done in the literature. But we wanted to be more explicit and then led to this. So the very conclusion of this paper is kind of intact. It's like, it kind of factors out, but
Yang-Mills theory, this is not done axiomatically. People really write formulas.
like Stiefel-Lichty class, what,
No. There's a version of this which people write down, which is,
I have never seen those.
you know, people put these things on the lattice. They measure their expectation value.
I see.
It's like a number, like 5.
Yeah.
So it's gauge invariant and it's sensible.
Yeah. There's a lot of this.
For instance,
Mhm.
if you can feed it to a computer and get a number, it's well defined.
Like the Wilson loop or the symmetry operator?
Symmetry operator, the utopia.
Mhm.
Like,
Like, is it like surface, like some of the star Fs?
of course. No, it's not some of star Fs, it's something slightly more complicated. I mean, it's some twist, you know, some kind of twist defect where you twist by elements of the same.
Yeah, but that twisting applies to the Wilson loops.
No, you can actually define this operator.
Yeah, but in terms of the twisting of the Wilson loops.
No,
You're
in
saying.
terms of the twisting of whatever variables your theory.
See, yeah, should you discuss after the talk or?
Right.
Let's see, yeah. So, all right. In this structure could be seen from the Lagrangian actually by noting the fact that the Wilson loop, the wired entity was secretly encoding the commutator structure. So if we work in the covariant phase space, and we kind of identify that symplectic structure, and from that we kind of know that, oh, to transform this A, we have to put some star F there. So roughly speaking, this is like encoding this commutator A comma star F equals to IH bar or something. So yeah. So with this insight, let me employ first order formalism to more manifestly, I mean, covariantly manifest this phase space structure. So if you integrate out the B field, the auxiliary field, and then you get retrieve the usual F squared Lagrangian of Yang-Mills theory. So in this case, the symplectic structure is like just given by B dA, which is kind of like P dx. So it is very helpful to visualize the structure like a seesaw like this. And then I will show that the symmetry transformation and topological symmetry operator is like kind of like leveraged by the seesaw structure. So let me show this explicitly. So with this first order Lagrangian and the symmetry operator in the first order formalism, where I just replace the star F with B, let me write the left-hand side in terms of the path integral in the path integral language. Amusingly, if I define the like a differential form analog of Dirac delta distribution like this, so that the surface integral becomes the integral over the whole manifold wedged with this 2 form, Dirac delta 2 form. And then amusingly, the symmetry operator gets merged to the e to the minus action term. And crucially, the twisted gauge transformation transforms the field strength with this additional omega inverse dd omega term. So if this omega was like just a usual single valued function, and then this double exterior derivative will be just 0. But it is multi-valued, and crucially, you can show that this combination omega inverse dd omega precisely equals that 2 pi lambda term. So if I use this twisted gauge transformation as a field redefinition, like the change of integration variable in my path integral, and then it precisely absorbs this term while transforming this Wilson loop. So yeah, this establishes that the twisted gauge transformation induces the transformation, the one-form symmetry transformation, by being kind of like governed by this BF structure. And note that this extra term, this B squared term, played like no role in this derivation. It's just there. It's just like a spectator. So we can summarize this story in this nice one slide, which is when we have like any Lagrangian, which is like BF plus some some top 4 functional of the B field, then we always have the transformed objects being the Wilson loops, and the symmetry operator being realized in this formula. Yeah. So with this understanding, now I will formulate gravity like in this form, like BF plus FB, and immediately identify the symmetry in the gravitational case. Yeah. So people say gravity is a gauge theory, but actually, if you really think about it, well, there are some subtleties. So for instance, if you think in terms of Lagrangian, I'm taking the Euclidean signature here. The Lagrangians looks very different. And mathematically, gravity, well, it has it is a gauge theory in the sense that it is a theory which involves a gauge redundancy, which is the diffeomorphism redundancy. But if we kind of restrict our definition of the terminology gauge theory to like theory described by the principal of fiber bundles, like gauge connection of the principal fiber bundles, and then no, the metric is not like it does not have the internal fiber structure, because the transformation of the mu nu indices here, they are the transformation of the tangent bundles, tangent spaces. They're linked or they're induced from the space-time diffeomorphisms, which shifts the base points. But for the Yang-Mills theory, we don't shift the base points, so they're different. And also in terms of perturbation theory, they are radically different. But Zvi will tell us that they are kind of secretly sharing some structure, which so that they can also all formulate it in terms of like cubic vertices. So with these inspirations and observations, we kind of deduce that to reveal the one-form symmetry, we seek a formulation of gravity in terms of a gauge internal group, not only the space-time indices. So a natural option to take is the tetrad formalism, where we formulate gravity as a gauge theory of local Lorentz group. So accordingly, the gauge algebra would be the Lorentz algebra. But the gauge group can be not only SO4, but it's quotients by some discrete groups as well. So I will discuss that shortly, because that's very crucial in the discussion of higher form symmetries. Secondly, we also seek for the first order formalism, because we gained the insight that this BF plus FB form kind of serves as the template Lagrangian for one form symmetries. So basically, we want to formulate gravity in terms of like first order tetrad formulation. So this is like a very brief recap of tetrad formalism, but let me just briefly point out the fact that the spin connection is given by given as the functional of the tetrad if we impose the torsion-free condition like that. So if we find the Riemann curvature 2 form, which is just the curvature 2 form of the spin connection as a gauge connection, and if we plug in the tetrad functional of the describing the spin connection to that formula, then we precisely reproduce the Riemann tensor found from the metric. So we can fix some numerical factors. So if we define G equals to square root of 8 pi G and identify that as the gravitational coupling, and then we can write down the Lagrangian for gravity in that nice form in terms of differential forms. But crucially, we can actually take the spin connection as a new degree of freedom, which is independent from the tetrad. And so why can't this work? So if we vary the Lagrangian with respect to the spin connection, and then you can show that the equations of motion imposes the torsion-free condition. So if you integrate out the spin connection and then you retrieve the usual tetradic Einstein-Hilbert action. Right. And furthermore, I can introduce the cosmological constant. But interestingly, if I define the so-called the Plebanski area to form, BAB equals to 1/2 epsilon ABCD E wedge E, and then the first term precisely becomes the form of BF, like BF B wedge F, and the second term precisely becomes the form of like B squared. So I can write down the Lagrangian form for gravity in this way, where here the anti-symmetrized local vector indices are identified with the adjoint index here. And I should also mention that there exists a formulation which is called the Plebanski theory, which takes this BA, which promotes this BA field to genuine fundamental degrees of freedom by kind of imposing a new constraint on this on the B field, so that it gets arise. It traces back to the tetrad like that. So so in that case, all the fields in the Lagrangian are only carrying the adjoint indices, and that actually kind of subtly changes the structure of the theory in terms of the one-form symmetry, but I will discuss it later. So the object is that we formulated gravity in this form, and which is surprisingly similar to the formulation of Yang-Mills theory in the first order format. So we kind of observed that those two are kind of like same theories, the same theory, in the sense that they all take this universal form, which is BF plus FB.
Are you talking like B equal to 0?
B equals to 0.
I mean, there was a question about whether like the gravity theory you want to.
Allowing B equals to 0.
Vertical,
right, like, yeah. So I think we don't necessarily meet that constraint, meet that condition. That's the invertibility condition for the tetrad. Yeah.
That's not really clearly the same theory.
Right.
Pardon? Then they're probably not the same theory.
Right. They're not the same theory, but in the sense that they all can be described in that form.
Yeah,
the same form. Yeah. So yeah. So this is actually very interesting for the double copy angle, and I will be happy to discuss later. Yeah. Right. So now we can straightforwardly import all the known results from Yang-Mills theory to gravity in terms with this observation. So for Yang-Mills theory, we discussed that the transformed objects are Wilson loops given by the line integrals of the gauge connection, while the topological symmetry operator is given by the surface integral of the B2 form. So if I just slightly change everything, slightly change A to the spin connection omega, and B to the Plebanski 2 form B, and then I can just immediately write down this formula. And here I unpack the adjoint index with to the anti-symmetrized vector indices with the canonical normalization factor of 1/2. And we'll see that the Lorentz group, the center of the Lorentz group, they are all like just plus minus ones. So so I should describe that in detail. So with the gauge algebra being the SO4 algebra, the gauge group can be either spin 4, which is SU2 cross SU2, or spin 4 modded out by Z2, which is SO4, and SO4 further modded out by Z2. And then the corresponding center groups are given by Z2 cross Z2 or Z2 or just a trivial group with only constituent being the identity. So as a zero form symmetry, this is counting the parity of the dotted indices, comma, the parity of undotted indices. And this guy is counting parity of alpha dot over alpha. And for Lorentzian signature, we lose the Z2 cross Z2, so we only have Z2 or trivial. So to make this symmetry non-trivial, and then we would want to make the gauge group take the gauge group as the take spin 1.3 as the gauge group. Yeah, and this Z2 is precisely encoding the double cover thing, the like the bell trick. So yeah. So the Wilson loop in this case, the Wilson loop of the spin connection is called the spin holonomy, and it's precisely describing the holonomy that you measure by parallel transporting a spinning top. So it also comes with various representations. So we can have it in the right-handed spinner representation, left-handed spinner representation, vector representation, and also a Joon representation. On the other hand, the symmetry operator is given by this formula, where lambda A is also exponentiating to a center element in the of the Lorentz group. So if I unpack the joint index into the anti-symmetrized fundamental indices, and then I can plug in the formula, the definition of the BAB for gravity here, which was the epsilon times E wedge E. And then I can observe the E epsilon to the lambda to make it the hot star. And then this formula, curiously, looks like area over 4G. So this combination is basically the dot, where this guy is just like the normalization. The inner product of this this lambda reference with this E wedge E, which is precisely describing the area element in the orthonormal frame. So this combination is precisely measuring the area of this infinitesimal area element of the surface in the direction of the star lambda AB. So, well, this was why I wanted to make it explicit, because the explicit formulation, the explicit formula is very suggestive. So it might be a coincidence, but yeah. But interestingly, it takes the form of area over 4G.
So I thought this would be topological.
Mm-hmm.
That's an area. So it's area of, sorry, what?
Yeah, so this operator, so my understanding is that if we computed this operator in some background tetrad, then this quantity will be not topological. But if you interpreted this formula as an operator that you insert in the path integral, and then it only topologically, it works like topologically, and it just implements the usual topological transformations of the Wilson loops. Now I will show that explicitly in terms of path integral later. Yeah.
So it's not really measuring an area; it's measuring.
Right. So we have to clarify this point. So actually, for Maxwell theory, we say that the symmetry operator is exponential of some integral star f, and we say that that is measuring the flux of star f, like the electric flux, the Gauss law. But it turns out that due to the Wallenberg coupling here, the correct interpretation turns out to be the opposite, actually. So when we have this view linking with W, we can interpret this as like the U measuring the flux of the W, but we can do in the other way around. We can also say that this W is measuring the magnetic flux of this U as a thin solenoid. And it turns out that the latter interpretation should be correct because of this 1/G coupling, and from the perturbation theory argument, which is like Dove construction of the geometry sourced by the symmetry operator. So yeah, I will elaborate on that.
But imagine there's no Wilson loop or no strength. Then in the normal Maxwell case, in the integral of star f is just 0. There's no flux.
Mm-hmm.
What is it here?
Yeah, it's not apparently it's not 0.
Also, presumably to be the area operator, you would have to do the same thing that I was complaining about before and make this gauge invariant.
Mhm.
Which, by the way, if you're looking at gravitationally inspired BF theory, there's a lot of literature on how to write these gauge invariant operators by averaging.
Mhm. Yeah.
The area is actually gauge invariant. It's not topological, but at least it's gauge invariant.
Well, the vector valued area, the area vector. But that carries like the vector index.
It's compounding too many problems for me.
So in the 3 dimensions, like if you think intuitively in 3 dimensions, this area vector is clearly topological. Like you can take any surface like this, but the area vector will be the same. But this vector is again in what frame are you computing this vector? Like,
Well, that's the gauge invariance complaint.
yeah. So this proposal is solving this problem by smearing this vector by the lambda. And and this was the only operator that we could prove that this operator, we want to find an operator that generates the one form symmetry transformation of the Wilson loops, and this operator was the only proposal that we could think of. So, but there should be more. Yeah, I agree. I agree that this is not entirely satisfactory. I'm very happy to discuss. I'll be very happy to discuss. Yeah, because clearly in the Maxwell case, you can just evaluate this symmetry operator and just get 0 or nothing, like for background with no insertions of other operators. But for Yang-Mills theory and gravity, well.
For Yang-Mills theory, you can also insert it and get 0.
Really?
I would very much hope so.
Yeah. You should tell that to me. I really want to learn. Yeah.
I've said everything I know.
Okay. Okay. Interesting. So yeah. Now I want to point out that this area is inherently chiral, because when we think deeply about the center exponentiation condition, then we kind of realize that to be exponentiated to a non-trivial center element, due to the in virtue of the very factorization of SO4 into 2 SU2 sectors, this lambda should be either self-dual or anti-self-dual. So it will be exponentiating to -1 in the left-handed sector or in the right-handed sector. So it turns out that any symmetry operator could be kind of decomposed into these fundamental building blocks, which I denoted as U tilde and U. And this guy is self-dual, right-handed, and this guy is left-handed. So this U operator will be transforming the alpha index, like the left-handed spin holonomy and the vector holonomy, while U tilde will be transforming the right-handed sector. So if you composed US and U tilde S, which is kind of like CPT invariant in the Euclidean sense, then the vector holonomy will be not transforming. So so let me now explicitly show the Ward identity. So this was the proof of the Ward identity for Yang-Mills theory, and I can just simply snap my finger and just have the derivation for the gravitational case. So perhaps this is not very helpful. So maybe it is more helpful to just extend out all the details and see how it works in the gravitational context. So the Einstein-Hilbert action is like some area 2 form, which the Riemann curvature. So if I inserted this symmetry operator, which I claim that it is to be given by the surface integral of the area form, And then if I insert in the path integral, and then this symmetry operator kind of merges with the e to the minus s, e to the minus action term. So we can factor out this area, and then what you get is the Riemann curvature minus the lambda times the delta function delta 2 form, which is precisely describing the surface support of the symmetry operator. And now I perform a twisted gauge transformation, twisted local Lorentz transformation on the state connection. And what we get is the transformation of the Riemann curvature with this additional omega inverse dd omega term, which would vanish if this omega was single valued. But I stipulate that this omega is like a multi-valued parameter. So so that this omega inverse dd omega describes the curl, like a non-trivial curl around the surface support S, so that this new term precisely cancels this part. Then what I get is the usual Einstein-Hilbert action inserted here, and then the transformed Wilson loops, transformed spin-Hall loops. Yeah. So now I finally can get to this point that I wanted to clarify earlier. So in Maxwell theory, we can interpret the linking, the wire identity in two ways. So first of all, we can say that, oh, this U, the symmetry operator, is measuring the flux sourced by the insertion of this Wilson loop. But also we can interpret that this wire identity is encoding the measurement of the Harnell bone phase in the thin solenoid generated by the symmetry operator. But crucially, because of this inverse coupling there, it turns out that the correct interpretation is only option 2 for non-abelian cases. So in Maxwell theory, trivial level is like just everything. So we can just like we could have had like both interpretations, but as far as we concluded, we think the interpretation that we should take is option 2. So in this case, we will.
Sorry, I'm confused. There's a coupling even in Maxwell theory. What's the issue?
Right.
Why do you care about this coupling?
Right. So yeah. So let's say we wanted to establish the wire identity by perturbative calculations. So then we will draw diagrams like this from U to W, and like this, and also but if you think about the coupling, and then here you have 1 over G, and the propagator carries like G. So this guy precisely can describe the linking because it has no dimensions. But here, here you also have 1 here, but so yeah. So this guy
So it's only a complaint about gravity or also about Young-Mills?
applies also for Yang-Mills.
But in Young-Mills it works. So let's be aware of it.
Well, I am still not understanding how the Gauss law interpretation works, so maybe I should learn.
Well, but it could be that these diagrams are 0 that you don't look. Did you evaluate?
Right? Yeah.
Fantasizing. There are lots of options.
Yeah, but for Yang-Mills theory, isn't this non-zero?
But this is not gauge invariant, so it's anything you want.
Right?
That's a key part of the discussion.
Yes.
The correct version of the operator is not some garden variety operator. It's a very special operator. So when you insert it into diagrams, there might be lots of cancellations.
See.
You could have said the same thing about any current, any charge. You can say that a current has correlation functions with lots of things. But then magic happens. Then when you integrate it to get a charge, lots of things cancel. And if you chase that in diagrams, it might look very complicated.
But they all cancel. So we should also like first make this operator make more sense. This operator.
That seems like
Yeah.
a good idea.
I totally agree. I totally agree. Okay. Right. So yeah. So now I want to to give a classical interpretation. I mean, sorry, a physical interpretation for the symmetry operator. And how can I do that? I just insert this operator to some background, and then see how that transforms, and interpret that as the geometry sourced by the insertion of that symmetry operator. And we already know that it is simply given by the twisted gauge transformation. So suppose we inserted, for simplicity, suppose we inserted the symmetry operator in flat spacetime. And then the transformation of the Riemann curvature will be it's like 0 plus this new term, which is precisely this. And if this was Yang-Mills, and then this will be describing like a Dirac string with some color flux. But in the case of gravity, that is describing like a sort of a cosmic string. So let me explain why. So first of all, it turns out that the metric is just flat, because if you just compute delta AB, EA mu, EB mu, and then the metric is not transformed, because crucially, the transformation is only acting on the local Lorentz indices. So G mu nu, which only has the spacetime indices, it is not transforming. So the metric is like just like left unchanged. While the torsion transforms linearly by this omega, and we only have one derivative, so the torsion-free condition is also preserved. But crucially, we can show that the algebraic Bianchi identity for the Riemann curvature just fails. We can just compute this quantity and explicitly show that it's non-zero. And crucially, the failure of Bianchi identity is signaling the presence of magnetic matter. So this string should be describing some exotic world-shaped source. So we can explicitly describe a stress energy tensor and also the magnetic stress energy tensor, which is just a violation of the Bianchi. And then it turns out that the magnetic stress energy tensor equals the magnitude of the magnetic stress energy tensor equals the magnitude of the electric stress energy tensor. So in this sense, we interpret this object as a string made of chiral matter. And in this geometry, let's say I put a spinning top, and its dynamics will be described by this equation, which is just the parallel transport equation for the spinner. Then it turns out that the spinning particle exhibits like a smooth precision on its axis to capture the factor of the Arnold-Bohm phase factor of rho alpha, which is like ±1. So the physical interpretation is that the smooth precision is precisely measuring the conical deficit angle in this geometry, and this object is creating like an exotic cosmic string made of chiral matter. So in this sense, we call this chiral cosmic string. So we can be further explicit. So let's say our multi-value transformation parameter is given by that formula, where the reference lambda is given by that matrix. Crucially, this matrix is describing rotation, like self-dual rotation in the tx and yz plane. But crucially, that direction is just completely independent from the actual directionality of the string in the spacetime. So why did this happen? Because we worked in the formulation where color and kinematics, like the spacetime and internal, just vectors off. So they are completely independent, which is very different from the usual cosmic string. So for usual cosmic string, the angle deficit will be only in the plane transverse to the string. But here, the two directionalities are completely independent. So you can explicitly compute the spin holonomies and verify that only the right-handed spin holonomy is transformed. We can be further non-trivial. We can put this chiral cosmic string in a space-time with matter or space-time with curvatures. So we explicitly put this cosmic string in an ADS structural background in our paper and verify that the spin holonomy transforms when it links with the symmetry operator. Yeah. Lastly, I will end with a brief discussion of symmetry breaking. So yeah. So in the framework of higher form symmetries, we say that the symmetry is explicitly broken if the Wilson loop is endable, because in that case we can just unlink the symmetry operator. Intuitively speaking, so it turns out that our defect operators or spin holonomies are endable by spinning matter fields. And while the screening of the vector holonomy is kind of automatic, it's self-screened by the presence of orbital angular momentum, like the operators like gradient reaching scalar times the tetrad. And this is kind of analogous to the self-screening of adjoint representation of Wilson loop in Yang-Mills theory. And also this discussion shows that there exists a new Z2 symmetry in nature below the scale of the lightest neutrino. Lastly, there has been a claim that all global symmetries are necessarily broken above some scale in a consistent theory of gravity, which are referred to as Swampland conjectures. So let's discuss like how this kind of conjecture interacts with our high form symmetries. So according to our proposal, there is a one form symmetry in dynamical gravitation. And according to the Swampland conjecture, we know that it has to be broken. So it could be either gauged or explicitly broken by spinning matter. And we kind of realize that our universe is follows this scenario where fermions exist. So another possible universe might be a universe with gauged one-form symmetry in gravity, but and it would be worth exploring that option in the future. Yeah. So to summarize, in this talk we derived or proposed a new one-form symmetry in dynamical gravity by working in lockstep analogy with Yang-Mills theory. And that was possible by observing two key insights. So first of all, we observed that the one-form symmetry transformation is given by a twisted form of gauge transformation. And secondly, we realized that BF plus FB serves as like a template Lagrangian for manifesting one-form symmetry. And we concretely derived this wired identity between the spin holonomy and the controversial operator encoding area over 4G, and interpreted this linking number vector as the geometric phase for a 180 degrees conical deficit angle. There are some very interesting future directions. So some straightforward directions would be generalization to higher space-time dimensions. And that in that case, the center group is more rich than the four-dimensional case. And since we worked in the context of EFT gravity with higher derivative, EFT gravity, which will admit higher derivative corrections, that is also a natural direction. But if we formulated everything in terms of BF, and then it will be like very straightforward to discuss those corrections. And also we can think about whether this construction of higher form symmetry can be done in other correlations of gravity. So for instance, there is like a very interesting correlation of gravity in terms of like purely in terms of connection variables. And also there's also a correlation called the McDowell-Manzuri correlation, which literally writes down Lagrangian of gravity equals F squared. and that's very interesting. So it'll be interesting to derive this symmetry in that context as well. And also there's a I mean in this part we only consider the twisting of the internal index, but we could have also thought about the twisting of the space-time indices. So in this case, it would be helpful to work in the metric affine formulation of gravity. More ambitious goals are like higher group symmetries and magnetic symmetries, or speculations of phases of gravity, but they have some subtleties. So I would be happy to discuss them later. And also, it would be interesting to understand the mathematical structure behind this construction, and also think about the connections to 3D case, where the Wilson loops link with themselves. But crucially here, we have the lambda factor in the symmetry operator. So intuitively, the linking between the Chern-Simons holonomies are kind of having E and omega at once, and they're kind of including the linking in terms of E and omega, but it'll be very more further insightful to understand this connection more explicitly. Yeah. So finally, I would like to propose a new direction as a further direction. So in this talk we focus on the BF structure to derive the gravitational one-form symmetry. But we could have also focused on the aspect of twisted gauge transformations. So in this talk, we consider the twisting of local Lorentz transformations, but we could have also thought of twisted diffeomorphisms. So what happens in this case? So if we perform diffeomorphisms and then twisted diffeomorphisms, and then it turns out that it precisely generates the so-called Misner string, which is the Dirac string defect for the top knot solution, which is identified as the gravitational magnetic monopole. And interestingly, recently I showed that the Kerr solution actually transformed to a very interesting configuration, which is two masses connected by a Dirac string. In stipulating this that this Dirac string follows like a adiabatic approximation in curved geometries, I could also derive some 4-point vertex for the Kerr. So yeah, so by the way, so basically here I'm proposing that there could be like algebra between gravitational singularities. Here we see that black holes are endpoints of a topological defect. So the old study of space-time singularities might be, there might be a new angle on the old study on spatial singularities in terms of our brand new exciting framework of higher form symmetries and topological operators. Yeah. Thank you for listening.